Okay. Hello, I'm Ta Kim, and today we'll be having a session on PyTorch, logistic regression, and MLP. So please make sure to download this file on Classum. And I'm going to run my code on my lab GPU server. So if you're using Colab, make sure to set the runtime type as Python 3 and GPU. So as you can see in this figure, more and more people are using PyTorch compared to TensorFlow, especially in research when building their AI models. So all of our lab sessions, all of our following lab sessions would be using PyTorch. First of all, we want to load our packages and set up our GPU. And we can visualize our current GPU server status using NVIDIA SMI. So please try running this code. If you're running on Colab, you guys would get something different with me because I'm running on my lab server and it shows all the GPUs my server has right now. And similarly, you can also use GPU stat, which is kind of more user-friendly in my personal opinion. I'll mute everyone. You can see that I'm currently running some other code on these GPUs, and these are the empty GPUs that I can use. I have memory on GPU 0 because I already set up this session on GPU 0. So now we want to set the GPU number, which we're going to run this session on, and we can do it using CUDA visible devices. We can set the GPU. I'm going to use GPU number 0, which is this one. But basically, you can use any empty GPU that you have. And if you're using Colab, then it would only show one GPU, so you can set it to 0. And today we're going to use mainly 2 packages, which are Torch and NumPy. So please install and import these 2 packages. We can try printing the PyTorch version. Mine shows 1.11. If you're importing the most previous one, then it would show 2.0.1. Installing might take some time, especially for Torch. And we'll move on to PyTorch, Tensors, and NumPy. So basically, Tensors and NumPy share very similar identities. They both store n-dimensional arrays, but the main difference is that tensors can be used for GPU calculation. And because tensors and numpys are both basically n-dimensional arrays, they share very similar grammar. And we're going to basically compare tensors and NumPys in this first section. First of all, you're going to define a NumPy array and PyTorch tensor using np.array and torch.tensor. Wait a minute, let me check if this is recording. Okay. And okay, so this thing is recording, and we're going to define our arrays using np array torch.tensor. Run this code. You would see one-dimensional array, and you would frequently want to check the shape or the size of the arrays, and you can do it with dot shape and dot size for tensor. So it shows that your size is 4. We have 4 elements here. And we also frequently want to concatenate 2 arrays. So we're going to concatenate the array 1 and 2. And for NumPy, we can use this concatenate function to concatenate these 2 arrays along our defined axis, which is axis 0. And in order to perform concatenate, we can use torch.cat. So try running this code. You would get the concatenated result of NumPy and torch. Now, you can also reshape your tensor. So we initially have 8 elements here, and it's one-dimensional. We want to reshape it into 4,2. And for NumPy, we can use reshape, and for torch, we can use view. We can also use a function called reshape in torch. It's similar to view, but it might create a copy instead of the original data. So if you run this code, you can see that the original array is reshaped into 4,2. So 4 rows and 2 columns. And there is this function called repeat in NumPy. If we run this repeat function, it would show the results over here. So it would repeat each element after themselves, which shows 1, 1, 2, 2, 3, 3 over here. And if we use the repeat function in torch, then it would show a different result. So 1, 2, 3 twice. And even though the function names are the same. For NumPy and Torch, they produce a different output. They're different functions. So it's very important to look at the documentations and search for what you want exactly. You would always have to look at the documentations for NumPy and Torch. And if you want to try to obtain the same results using Torch, the same results as NumPy here, then you can first modify the shape into 3,1 over here. So this is the initial X. We can change the shape into 3,1. And then we can repeat this tensor 1 times along the 0th axis. So for this one, you only want one row. And we want to repeat it twice along the first axis. So 1, 1 here. And this repeat output would show like this. Now we want to flatten this result into 1 dimension, and we can use it by performing this, view -1. And it shows the same result as the NumPy result over here. So try running this code. And I'll move on to stack. So torch.stack explicitly stacks this tensor. So we want to stack X 4 times. We're going to do it by torch.stack, and the stacked results are showed here. So we're stacking this 4 times. And we can also perform repeat, which repeats this 4 times. So as we saw in the example over here, it repeats 1, 2, 3, 4 times, which shows this result. And we can get this stacked result using repeat and view by first repeating this 1, 2, 3, 4 times. And then we want to make the shape into 4 times 3, which shows this result. And it's identical to this stacked result over here. If any of you have any questions, you can leave it in the chat box. And we had some feedbacks that the lab session was a bit fast last week, so I'm trying to slow down. And so in this first session here, we dealt with NumPys and tensors. And they both deal with n-dimensional arrays, and tensors are used for GPU calculation. So all the codes here were run on, if we check the device, it's run on CPU. And now we want to make our tensors run on GPUs. So we're going to see how to do this. First, we can check if it's currently possible to use GPUs. So if our server has GPUs, we're going to check if CUDA is available. And it says true because my server has GPUs. And we're going to define two variables, A and B. And if we try running the device, it shows that both variables are on CPUs. This is the default device. And we're going to try adding up A and B into C. And if we check the device, C is also on CPU. So two variables on CPUs added up to a variable on CPU. And now we're going to move variable A and B from CPU to GPU using .to CUDA. So if you run this code here and check the device, it says CUDA 0 because over here, we set our GPU number to 0. We're gonna use GPU 0, so that's why it says CUDA 0. And we can also move our variable from GPU to CPU using .to CPU. And if we run the device, it says CPU. So it was initially in CUDA 0, but now we moved it back to CPUs. If yours says false. So if CUDA torch.cuda is available says false, it means that you need to set your runtime type to GPU. So in Colab, you can set your runtime type to GPUs. And yeah, I hope that solved your problem. And for Autograd, we're gonna use PyTorch Autograd. It is a package that allows automatic differentiation of tensors. And we would use Autograd when we're back propagating our model. So if we want to back propagate and train our model using gradients, then we would use Autograd. So torch.ones 2, required grad equals true. It shows a tensor here, and the requires grad equals true. This means that we're going to track all the operations on this X. And we're going to create a variable Y, which adds 2 to X. And it shows 3 here. Now for this variable Z, we are going to get the results here. 27. Y times 3. And then we're going to apply this mean function to our z over here, which gets the mean of z. So it adds up all elements and divides it by 4. Now, we want to explicitly print all the gradients for y and z. So that's why we're performing retain grad here. And if we try out dot backward, it would now do a backward pass. And we can check the gradients of x, y, and z using dot grad. So for Autograd, it's used for differentiation and backpropagation, and we can check our gradients for each tensor using dot grad. Now, we can use torch.nograd when we're very sure that we won't do any backward pass in a block of code. So when we're performing testing, we're sure that we won't update our model. There won't be any gradient computation. So the block of code that we're performing testing, we can wrap it with torch.nograd. And this means that all the codes here would not require any gradient computation. So if we run our code wrapped on torch.nograd, we can get the output as tensor. And when we try to run this dot backward, it would show an error because we wrapped it with torch.nograd. And the reason why we would want to use torch.nograd is because it saves memory and it's faster. So if you're very sure that a block of code does not require any backward computation, then just wrap it with torch.nograd. And some use cases would be your test code. Retain grad is not essential for backpropagation. It's just because I want to see the gradients of y and z, which are not the leaf nodes. We would basically use no grad. We wouldn't use no grad for training most of the time. Which situation would be to detach a computation or from the computation history? Yes, this is also for efficiency purposes. When you're sure that you won't need to detach anything, when you're sure that you won't need to backpropagate, then you can use no grad or detach. And we're going to work on nn.module. So first, import torch.nn. This nn.module is used for neural networks. So until now, we basically dealt with tensors on CPUs and GPUs, and Autograd, which is for backpropagation. Now we're gonna work on neural networks. So import torch.nn as nn and define a tensor x. So this is the x tensor and this is the shape. And we want to define a linear module. Linear in this variable. So this is our linear function over here. And we created input x. We want to put it through this function. And it shows the result of y over here. So our initial input data was 2, 3. We put it into 3, 1 linear module. And now it shows the y output as 2, 1. And we can also get the sum of y using y.sum. So we can use predefined modules in PyTorch, such as nn.linear. And there are also different types of modules defined in PyTorch. We can use transformers, GRU, RNN, LSTM, and CNNs. So we would basically most of the time be, for simple modules, we would stack the predefined modules from PyTorch and create our own module. Now this is an example here. We want to design a customized model, and we want to first define 2 linear layers and a ReLU function. And we can use these predefined modules down here to explicitly set the order in which we place the layers. So first we want to make input x go through linear 1, which is defined in this init function here. And we want the output of x go through ReLU. And then the output of ReLU go through linear 2. Okay. And so ReLU is an example of an activation function, and it lets the input go through nonlinearity. So there are many different functions which are activation functions. So this was nn.module. We can use predefined modules from PyTorch, and we can design our customized model using these predefined modules. Now we're gonna perform MNIST classification with PyTorch. So here are the packages that we're going to import. We're going to import NN and data loader, torch vision, transforms. And we want to load our data sets for training and testing. So first load the train data set and then the test data set. We're going to use MNIST. And so this is the code for loading our data sets. And this is the code for defining our data loader. We want to create a train loader and test loader using train data, test data with a batch size of 128. And we want to shuffle for training, and we don't necessarily need to shuffle for testing. And for the batch size, usually we would set it based on our GPU memories. So we would set a batch size that fits into our GPU memory. So first load the train data, test data, and define our data loaders. And we can define our model. We're going to use a one-layer classifier. So in this init function, we're going to define a function that we're going to use in this forward function. So we're going to define a linear layer and then dot linear with our input size and output size. And using this defined layer, this is the function that runs when we put our input X into this class instance. So if we input X, then this forward function would run, and it would go through our defined linear layer and return the output. So define this customized model. We're using the predefined nn.linear here too. And generate the model. This is a model instance. We want the input size to be 784 and the output size to be 10. This is our model. If we print our model, it shows that it consists of FC, which is a linear layer of 784 and 10. And we want to run our code on GPUs, so we need to move our model to CUDA. And we need to define our optimizer, which optimizes the training. So there are different optimizers such as SGD, Autograd, Atom, and we're going to use SGD here today. We're going to input our model parameters, set our learning rate, and momentum. So this optimizer makes sure that our model is trained so that the loss, so that we're moving our model parameters in the direction that the loss function is minimized. And these different optimizers have different properties, so you can use an optimizer that best suits your purpose for the model. This is a small image that shows how the model parameters are optimized. So until now, we loaded our packages, set our data set, train test loader, defined our model, and created a model instance, and defined our optimizer that optimizes our training. Now we are going to train the model, and we're going to use cross entropy loss because we're performing classification on MNIST, and the total steps are the number of steps in train loader. So we'll set the epoch to 10, and we're going to go through our train loader batch one by one and load the images and labels from this train loader to GPU using .CUDA. And then, so these are the images and labels in our current batch. We're looping through each batch in the train loader. And we're going to input the images to our defined model. So this is our model instance. This one layer classifier. We are going to put our images through this model and get the outputs. And we're going to take these outputs and the labels. These are the answers to the classified images. So we're going to input the answers and our model outputs and calculate the loss using cross entropy loss. And first, we want to make sure that we zero out the gradients for optimizer, because if we don't do this, then the gradients would be accumulated, but we only want to compute gradients for this round. And we zero out the gradients, and then we perform loss dot backward. And this does a back propagation based on our loss function. So it makes sure that, so it computes the backward pass of this loss function. And we step through the optimizer. So this is the gradient calculation step. And this is the step where we explicitly update our model parameters. So we have our input data and put our images through our defined model. And then based on the outputs, we get the loss. We first clear out all the gradients so that only the gradients of this round would be left. And we do a backward pass based on this loss function, calculate the gradients, and we move the model parameters so that based on this gradient calculation. So we're moving the parameters so that the loss function in the direction that the loss function is minimized. And we want to print each epoch. This is just for printing our losses and our steps. So this is basically our training code. So if we don't do zero grad, then the gradients from the previous step would be left, and we don't want that to happen. And then we want to test our model using torch.nograd because we're sure that we won't do any gradient computation in our testing stage. So for each batch in the test loader, we loop through the batches and get the test images for this current batch. And we, similar to the training process, we input our images to our model instance, get the output, and our outputs are a soft value. So we want to make sure to get the predicted results based on this torch.max. So we would get our hard predictions using torch.max over here. And in order to get the accuracy, we would need to get the total number of instances and the number of correct instances. So we compare the predicted results and the true labels, which are the answers, and get the number of correct items. So it shows that our test accuracy is 92.33. And we can make our model a bit more complex because this test accuracy is not that high. We only used a single linear layer. So we want to make the model a bit more complex. The accuracy is slightly different, but do we not know how much it is? The accuracy might be different because our seeds are different and our torch versions are different. So it might be slightly different. And that's why when we're doing research, we would set the seeds so that each time we run the code on that particular seed, it would always result in the same result. And we would perform multi-seed computation and average up the results. And so we're gonna make the model a bit more complex using 3 fully connected linear layers and sigmoid. So we want to define the functions that we use up here in this init. So when we create an instance of this model, these instances would be created based on this input size and hidden size and output size that we put in here. So these would be created when we generate an instance of this model. And when we do a forward pass down here, that's when this forward function would run. We have our input x, and this x would first go through FC1, and then take this output, put it to sigmoid, take the output, put it to FC2, and yeah, get the final results based on this order. Now down here, we have our neural net model. This is a model instance. From here, we put our model to GPU because we want to run on GPUs. And so if you run your code on GPUs, you need to put your model and your input data on GPUs. That's why we're doing 2 CUDA on the model and the datas. And we're defining our loss function using cross entropy and our optimizer as SGD. You can try using a different optimizer, such as Atom. And this learning rate and momentum are basically hyperparameters. So you can get better results by tuning these parameters. So we get the number of steps for the train loader, and we're gonna train this model 10 times. So for the whole train loader data, we're running it, the whole train data 10 times. And for each time we run this train data, we're gonna run based on each batch. So we have our images and labels of our current batch here. We put it onto CUDA and then put the input images to our model instance, get the output results. And then we put, based on our outputs and our true answers, we put these 2 into our loss function. And then we want to make sure to zero out the gradients and perform backward computation based on our loss. And then, so this is the step for gradient calculation, and this is the step for explicitly updating our model parameters based on these gradients. And this snippet of code is just for printing our train status. So if you try running, okay, I didn't define this. If you try running your code, the loss is decreased in a way faster speed compared to here. So we are currently training our model with 10 epochs. And we can perform testing using torch.nograd. So we loop through each batch in the test data and get the images and the labels, put them on GPUs, and then we put these images to our model, get the output, and in order to get an index, a list of indexes that are predicted, we perform torch.max for classification. And based on these predicted results, we get the number of correct values and the total number of data in this batch. We're adding them up and we get the final accuracy after this for loop is computed. So after we loop through all the test data. And you can see that we get a slightly higher accuracy. So for better, you can actually, this is a very simple model over here. You can, to get better accuracy, you can try building your own model and train the model with similar steps over here to get better accuracy, maybe modify the layers, type of activation function, or type of models. And you can also optimize your configuration. So these are hyperparameters such as like learning rate, epoch type, or type of optimizer. And this is a way that you can squeeze for better performance. Okay. So if you have any questions, you can put it in the chat box. After we send the data to GPU, it seems that we don't need to later free it from GPU. Is it done automatically? Oh, okay. So we would only use GPUs when we run this code. And after running this code, the memory would be put out of the GPUs. So we don't explicitly need to free it. Okay, for Jupyter Notebook, I actually don't use Jupyter Notebook, but if you're running your code on Jupyter Notebook on your server has to have GPUs. If you want to use GPUs for running your Jupyter Notebook. But yeah, I'm not too sure with Jupyter. So I'm not too sure whether Jupyter provides GPUs. So maybe you can try running on Colab. Okay. For random seeds in PyTorch, you can explicitly set the, I think it was random seed function. You can try searching for the exact function, but in order to get reproducible results, you need to make sure that to fix the NumPy and the torch and all the seeds that you're using during training. Okay. default device to CUDA. Most of the time we would just use dot to CUDA. So maybe I'll go through a very quick overview of what we did today. So first, we checked our GPU status using NVIDIA SMI or GPU stat, and we set the GPU number that we're going to use using CUDA visible devices and import our necessary packages. PyTorch tensors and NumPys, they both store n-dimensional arrays. And for tensors, this is used for GPU calculation. And NumPy's tensors share very similar attributes, and some grammars are the same, but some grammars are different. So you need to make sure that you always check the documentations for NumPys and PyTorch. And so these are all the different operations using NumPy and PyTorch. And then if you want to use your tensors on GPUs, check if GPU is available. And you can move the tensor from CPU to GPU using toCUDA, and you can move your tensors from GPUs to CPUs using .cpu. And then there is Autograd, which performs automatic differentiation when you're backpropagating your model. And you can get to your computed gradients using .grad. And by setting torch.nograd, you can save memory and make the computation a bit faster. So if you're sure that a code block does not require any backward passes, then just wrap it with torch.nograd. And if you do that, then you cannot do any backward. Next, we worked on nn.module. So there are many default NN modules in PyTorch. You can check out the documentations, and one example is nn.linear. So there are CNNs, RNNs, LSTMs, GRUs, transformers, and in the following lab sessions we would be dealing with these modules. So we would be creating a model, a customized model with these modules. And we can also define our customized model by using nn.module. And we need to define our init function and forward function. And whenever we create a model instance, then this init would run and it would create these linear and ReLU that we defined. And then when we explicitly put our input data and run this model instance that we created, then it would make sure that the inputs X go through these steps and return X. Next, we worked on MNIST classification with PyTorch. So first, load your necessary packages. And load your dataset, train loader, test loader. So for this MNIST dataset, they explicitly divided the train and test data for us. But if you recall from the last lab session, we actually loaded a single data and split it into train test. So that would actually be the usual process. But for MNIST, they created a train and test data set for us so we can just load the train and test data sets. And we would define a data loader, which splits the data into batches. And whenever we train the data for each epoch, we would run through one batch at a time. Okay, and we can define a model like this. It's a very simple model. We defined an nn.linear and a forward function that uses self.fc. And then generate a model instance, 784, 10, input size, output size. It would create an instance. And this is also created in this stage. We get our model, put our model to GPUs, define our optimizer, and then we train our model. We can set the epoch to whatever we want. But we need to make sure that it is sufficient enough that it trains. And for each epoch, loop through each batch in the train loader, get the inputs, put the inputs to our defined model, get the outputs, and compute the loss, clean the gradients, do a backward pass, and update the model parameters. For testing, we use torch.nograd, and we loop through each batch in the test loader. And then this is just a more complex model than before, but this itself is also a very simple model. And then the training steps are identical to the previous steps we saw above. And then using torch.nograd, we test our data. We test our test data on our trained model. Okay. What is an elegant way to create validation set for MNIST? So I'm not sure if they provide a validation set or not, but if they don't, then you can actually create it with this test data set over here. You can you can split this test data set into valid and test. Or if this test data set is too small, then you can actually take parts from this trained data set to create a valid data set, but you need to make sure that the valid and test data are not mixed during training. So you should not be using the valid and test data for training the model. So do you guys have any final questions? Okay. So next week there would be another TA, and next week there's going to be another TA coming, and I'll be coming back maybe sometime during the middle or the end of the semester. And I think we can end here. So thanks for your participation and see you guys next week in our lab session. Okay, thank you.